Hello there, Mr. Sutton here with the AB Calculus 4.4 homework solutions on concavity. For this problem, they're telling us for all x on the interval 2 to 5, the function f has a positive first derivative, negative second derivative. We want to pick the table that matches that function. So just writing it symbolically, they're telling us that f of x, or f prime of x, is greater than 0, and f double prime of x, the second derivative, is less than 0. Well, what does that mean? It means that the function f, because of f prime being greater than 0, f is increasing, but since f double prime is less than 0, we're increasing at a decreasing rate. So we're increasing the function, it's climbing, but it's slowing down. So which answer matches all that? Let's look at each of them and see what we can eliminate. So choice A, we go to 7 to 9 to 12 to 16, so that's definitely increasing. Now, how much are we going up? We go from 7 to 9, that's an increase of 2, and then 9 to 12 is 3, 12 to 16 is 4. So we're increasing, but we're increasing at an increasing rate, not a decreasing rate. We're not slowing down. So this cannot be the answer. Choice B, we're going from 7 to 11 to 14 to 16, so again, increasing. Now we have an increase of 4, followed by an increase of 3, and then 2. So increasing at a decreasing rate. Well, that's exactly what we were looking for, so that could be a table of values for f. So that's a good answer, but let's just make sure there isn't anything even better out there. So if we look at C, we're going from 16 to 12, so we're decreasing. Table D, same thing, decreasing. And same thing in E. In all of these answer choices, we're not even increasing at all, we're decreasing. So these are all solid no's. That means that choice B is our answer. On this problem, we're given the function f of x equals 3x to the 5th minus 20x cubed. We want to find all x values where this graph is concave up. So basically we're asking, where is f double prime of x, the second derivative, where is that positive if we have concave up? So let me find the first two derivatives here. F prime, the first derivative, that's going to be 15x to the 4th, just using our power rule here, minus 60x squared. And we need to go one more derivative now. So f double prime, that's going to be 60x cubed minus 120x. And now we need to find some critical values so we can see where this thing changes, negative versus positive. So I'll set it equal to 0, and I can start the process by factoring out, it looks like a 60 and an x. That will leave us with x squared minus 1, or actually x squared minus 2. So x squared minus 2, all that equals 0. So we see that this is all going to equal 0 whenever x equals 0 for this 60x piece. And with this parentheses here, if I add 2 and square root, I've got plus or minus radical 2 as my other two critical values. So let me make an f double prime number line now and put my critical values on there. So going from left to right, I have negative radical 2, 0, well, this 0 right here, and positive radical 2. And now testing out something in each of these four intervals, so a lot of sign analysis going on here. Something less than negative radical 2. Well, negative radical 2 is less than negative radical 4. Or actually, it's greater than negative radical 4. Negative radical 4 is to the left of this. Negative radical 4 is really just negative 2, right? So if I test out negative 2, that's definitely to the left of negative radical 2. All right, so I'm going to test that out in this factored version of reality here. So that's going to give me a negative on the outside, and this is essentially 4 minus 2, which is a negative on the inside, or a positive on the inside, rather. So negative times a positive is going to give us a negative. Something between negative root 2 and 0, how about negative 1? So that gives me a negative outside and a negative inside, because inside we've basically got 1 minus 2. So negative negative is positive. Plugging in positive 1 now on the other end here. I've got a positive and a negative, so negative overall. And let me plug in positive 2 or positive a million, whatever you want over here. So that's a positive times a positive is positive. Concave up, we're looking for the positive f double prime intervals. So that means that f is concave up from negative radical 2 to 0, union radical 2 to infinity. So putting that in standard inequality notation to match an answer choice, we have negative radical 2 less than x less than 0. And let's see, it looks like the only answer choice with that is choice B. And this last piece here, this would be x greater than radical 2, which we also have in choice B. So B it is. For this problem, we want to know where the graph of negative 5 over x minus 2 is concave down. So we're basically asking where y double prime is negative. And to figure that out, we need to know y first prime first off. And before we can even do that, I'm just going to convert this into something that's easier to work with. Because right now, if I take the derivative, I'm going to be using the product rule, which is kind of nonsensical when you have a constant in the numerator. So I'm going to turn this into negative 5 times x minus 2 to the negative 1. Now I can just use the power rule. So this is going to be, for our first derivative, positive 5 times x minus 2 to the negative 2. And then one more derivative, that's going to give me negative 10 x minus 2 to the negative 3. I am going to turn this back into fraction mode because it's easier to find critical values in that mode. So I can rewrite this as negative 10 over x minus 2 to the positive 3. And in terms of finding critical values, we have critical values in general where the second derivative is 0 or undefined. This, however, can never be 0 because we don't have a variable in the numerator and the numerator is not 0. However, we can figure out where this thing is undefined. Y double prime will not exist where x equals positive 2. So this gives us something to do some sign analysis around. Getting my number line here, this is a y double prime line with x equals 2 is the only critical value. Let me plug in something a little bit less than 2, like 1 or 0 is even easier. Now, taking a look here, this is going to be a negative over, let's see, 0 minus 2 is a negative cube. That you still have a negative. So negative negative gives me a positive. And then plug in something bigger than 2, like 3. Automatically negative numerator. Downstairs we've got a positive now, so that's a negative overall result. We wanted concave down, so that's going to be x greater than 2, which is going to give us answer choice E. For this problem, we want to know which of the following is true about the graph of y equals ln of x squared minus 1 inside absolute value on the interval negative 1 to 1. And this was a no calculator problem, so just taking a look at the answer choices here, we're talking about the function being increasing, having a relative min. We're talking about the range of the function, where it would be helpful if you knew if there was a min and max at this point. And then we're also talking concavity and asymptotes. So we're talking about pretty much this function at every single level we could possibly analyze it. Let's start with the bottom level. If we have an asymptote at x equals 0, that means if I plug in 0 for x up here, at the very least I ought to get undefined. So let's see what actually happens if I do y of 0. So that's going to be ln of absolute value of 0 minus 1, so an absolute value of negative 1. Well, that's just really ln of 1, which is the very real number 0. So that means essentially that y is defined at x equals 0, so there can't be an asymptote there. So choice E, we can actually eliminate that pretty quickly. Now for all these other ones, we're going to need a couple derivatives. Let's take the, before we can take the first derivative, we have to deal with this absolute value. It's really a pain to take the derivative of something with an absolute value if you just leave it there, because then you have to set up a piecewise function and establish continuity at border values. So if we can do this without having to go through those jumps, jump through those hoops there, we'll be in better shape. Now the key on this is I'm on the interval from negative 1 to 1. On that magic interval, I'm plugging in numbers between negative 1 and 1, which means that inside here, if I'm plugging in numbers between negative 1 and 1 and squaring them and then subtracting 1, I'm always going to be doing something smaller than 1 minus 1, which is to say I'm always going to get a negative answer out of that. Since we're guaranteed that this stuff inside is always going to come out negative, between negative and positive 1, in order to simulate absolute value without actually having it there, I can negate everything inside, which I could also just do by switching the order of subtraction. So I'm going to write this instead as ln of parentheses 1 minus x squared. And now when I plug in numbers between negative 1 and 1, I'll just get a positive version of whatever this original statement would have given me. Okay, so the reason we did all that is so we can take the derivative of this. So y prime is going to be, using our derivative rules, we're going to have 1 over 1 minus x squared times the derivative of the inner function. That's going to be a negative 2x that we're multiplying by, and I'll just put that directly in the numerator. So now I need to find critical values for this thing. So that would be anywhere where this equals 0 or does not exist. Negative 2x is the only piece that we're worried about with the 0 part. If negative 2x has a value of 0, that's going to happen when x is 0. So we have a critical value there. And we also see that this function is going to be undefined. Y prime is undefined when x is positive or negative 1. But since those are our endpoints, I mean, we'll list them as endpoints on our sign analysis, but we don't actually have to worry about testing around them too much. All right, so let me make my y prime number line here. Again, I'm going to use negative and positive 1 as endpoints. And the only reason I'm putting them in here is so I don't accidentally test something outside of this interval, because that might not give me the same results as something inside. And we also have that critical value that we found before at 0. So testing something between negative 1 and 0, like negative 1/2, plugging that in here, that's going to give me a positive in the numerator, and I've got 1 minus something less than 1, so that's going to be a positive in the denominator, positive overall. Testing something now between 0 and 1, how about 1/2? Negative numerator, positive denominator, gives me a negative overall. So I see here, and I'm going to write something that wraps up several answer choices now. I've got a y prime that is positive from negative 1 to 0, and then y prime is negative from 0 to 1. What this means is that y is increasing until we get to 0 and then decreasing after that, at least until we reach those border values there. So this establishes a few things. For one thing, y is decreasing. Y is decreasing from 0 to 1. Well, if y is decreasing on a piece of this interval, we can't say, like we did in choice A, that it's increasing across the whole interval from negative 1 to 1. A piece of this is not true, so we can eliminate choice A. Something else important coming out of this is, since I'm increasing until I get to 0 and then decreasing after that, well, that means that the highest point on this interval occurs at x equals 0. We have an absolute max at x equals 0. Another way of thinking about it is this is the only critical value and it's a local max. That makes it an absolute max. Anyway, that means that it cannot also be a local min. Choice B, they said a relative min at 0, 0. Well, you can't have a relative min at the same place you have an absolute max. That makes no sense. So B is gone. Also, if we have an absolute max, that means that our range in this interval cannot be all real numbers. The range is talking about possible y values. Well, you can't get all y values if you're going to stop somewhere at some y value at 0. We don't know what the max is yet. I mean, we could plug it in and find out. Actually, we do know. It's 0. But anyway, yeah, our range is not all real numbers. So C is also out. Well, just taking a look here, we've eliminated E earlier, A, B, and C. That means it's going to have to be choice D. But if you're not sure, we can always test out that theory. For that, we would need the second derivative. And since the first derivative is a quotient that we can't really reduce, I'm going to need the quotient rule to take the second derivative. So let me get out my box and ribbon for this. Negative 2x, my numerator, and 1 minus x squared, my denominator, goes here. Derivatives are going to be negative 2 and negative 2x. Using the ribbon to multiply all that out, I'm going to have, let's see, negative 2 times this stuff. So that's negative 2, and then I'll just distribute it here, plus 2x squared. Going back the other way, we've got negative 2x times negative 2x, which is positive 4x squared. Actually negative because we're subtracting, right? So 3 negatives gives us a negative overall. And then up here, this 1 minus x squared, that's the v squared that's being squared down there. Cleaning this up a little bit, we can combine these x squareds. This is negative 2x squared. And one thing that's going to make my life a little bit easier, if I factor a negative 2 out of that numerator, leaving me with 1 plus x squared. That's going to make our sign analysis a little bit easier. Now, before you find critical values and start doing sign analysis, take a look here. I mean, negative 2 is obviously always negative because it's a constant. 1 plus x squared has to be positive. Squaring something makes it positive, and adding 1 keeps it positive. So our numerator always is going to be a positive or a negative number. It's going to be a negative times a positive. The denominator, you're squaring whatever comes out of this parenthesis, so that's positive. So we have a negative, a positive, and a positive. That's always going to be less than 0, at least as long as x does not equal negative or positive 1, because that would make it undefined. But any numbers but those are going to make this whole thing come out negative. That means that y is concave down on the interval that they mentioned from -1 to 1. So that confirms answer choice D. For this problem, we are given the first derivative of a function, and we want to know on what intervals the original function is concave up. So basic idea is we just need to figure out where the second derivative, f double prime, is positive. If we've already got f prime, we just need to take one more derivative to get f double prime. So using our power rule on each of these terms, we've got 4x cubed minus 12x minus 8. And we're going to figure out where this equals 0 to get some critical values, and then we'll just use the graph to see where this thing is positive or negative. So let's go to Desmos, because this is a calculator question. So on Desmos, let me just graph this. We've got, I'll just call this G. So we've got 4x cubed minus 12x minus 8. And let me move this so I can actually see it. And there's my graph. It looks like if I zoom out, those are the only critical values, and that's happening at -1 and +2. So here's a snapshot of what I just got. I see that -1 and 2 are my critical values, and I can use the graph here just to do some sign analysis. So until I get to -1, f double prime is negative. It's still negative after I get to -1, still below the x-axis, and then it's positive after I get to 2. So since f double prime is greater than 0 from 2 to infinity, that's telling us that f itself is going to be concave up from 2 to infinity, which is going to give us choice A. For this problem, our function is defined as this cubic polynomial. We want to know where the graph of this thing is decreasing and concave up. So we're going to have to do 2 levels of sign analysis. We need the first derivative to figure out the increasing versus decreasing part, second derivative for the concavity. So let me start by getting f prime. That'll be 6x squared minus 6x minus 12, and then that 18 becomes a 0. So let me find critical values here. I'll set this equal to 0. And in terms of solving for x, I can factor a 6 out of all this. So that's x squared minus x minus 2 inside. And now doing a little more factoring, things that multiply to -2 and add up to -1, that would be +1 and -2, so x plus 1, x minus 2. This is a true statement where x is -1 or 2. So those are our critical values for the first derivative. So here's my f prime number line, -1 and 2 for that. And let me test some number to the left of -1, like -2. That gives me a negative and a negative, so that's positive. Between -1 and 2, we've got 0. That's a positive times a negative, so negative overall. After 2, we've got 3. Positive, positive is positive. And all I care about is decreasing. That happens wherever f prime is negative, so that would be between -1 and 2. Okay, now we need to figure out concavity and see what interval of concave up overlaps with this -1 to -2 interval. So for this, I need the second derivative. Here's my first derivative. The second derivative will be, using our power rule, 12x minus 6. And then I want critical values for this, so I'll set this equal to 0. This one I don't have to do any fancy factoring, just add 6 and divide by 12. So that's going to be x equals 1/2. Putting that on an f double prime number line now. Something to the left of 1/2, well, how about 0? Plugging that into my second derivative right here, that's going to be 0 minus 6, which is negative. And then something bigger than 1/2, how about 1? 12 minus 6 is positive. And we wanted concave up. So that's going to be the positive interval, 1/2 to positive infinity. So we still have to figure out where these things overlap. Well, I'm good between -1 and 2 for the decreasing end of this. But only once you get to 1/2 are you also concave up. And you're not decreasing once you go past 2. So then from 1/2 to 2 is that magic interval where we are both decreasing and concave up. So that's going to give us choice D. For this free response problem, we're given this f function, x squared minus 2x minus 1, all of that times e to the x. So that's a little crazy. This is a no calculator problem too. So we're going to have to be good at our analysis here. For part A, we just want the limits as we approach infinity and negative infinity. Well, as we approach infinity, basically we're doing infinity times infinity, which I'm not going to write because that's mathematically suspicious. But we have this polynomial here that is growing without bound times an exponential that's growing without bound. Multiplying that gives me more infinity. So our right side limit at positive infinity is just going to be infinity, or you could also say does not exist. Infinity is just a form of does not exist. Negative infinity, a little bit trickier, and that's because we have this exponential term. The negative infinity doesn't really affect the polynomial as much. Your dominant term here is still going to be x squared, and plugging negative infinity into that would give you an infinity. However, if you plug negative infinity into e to the x, you've essentially got 1 over e to the positive infinity, which behaves differently. So to make more sense of this problem, I'm going to convert things a little bit. Instead of approaching infinity, negative infinity with positive x, I'm going to make this a negative x and approach positive infinity with that. So for my negative infinity, I'm going to rewrite this as the limit as x approaches positive infinity, and now I'm going to negate all the inputs. So when I plug positive infinity into all these negative x's, I'm essentially going to be finding the limit at negative infinity. This is just another way of writing it. Now the reason I'm writing it this way is now I really feel justified with moving this e to the x into the denominator. So my denominator then is going to have an e to the x in it. My numerator is just going to have the dominant term from this polynomial, which if I square negative x is just going to be x squared. And now choosing between these functions, I know that e to the x is a faster growing function than x squared. So that's going to, since this is a bottom heavy function, that means this automatically goes to 0 for the limit to infinity. And that ends up being my final answer, limit equals 0 here. For this part of the problem, they want to know the intervals on which this function f is increasing. Show the analysis that leads to your answer. So we're basically trying to figure out where f prime is positive, which means we need to take the derivative of this. This is a product, so we're going to use the product rule. So let me break out the box and ribbon here. I have factors of x squared minus 2x minus 1 and e to the x. Derivative of our polynomial is just 2x minus 2. E to the x is its own derivative. Multiplying this out, I've got 2x minus 2 times e to the x plus all this stuff times an e to the x. Now sometimes I distribute when I multiply things out with my ribbon, but I'm actually going to leave things unmultiplied, and you'll see why I do that. So first term is just this stuff times e to the x plus all this craziness times another e to the x. And at some point I need to set this thing equal to 0 and find critical values. Now the reason I left it undistributed is these two terms here have a common factor of e to the x that I can factor out of here. And what does that leave me with inside? Well, I'm going to have this 2x minus 2 part plus everything that was in this parentheses. I can now combine some like terms and simplify this a little bit. Might make it easier to solve. So I have an e to the x outside. Inside I have an x squared. And combining the 2x and the negative 2x, that actually zeroes out. So all that's left is this negative 2 and the negative 1, which give us negative 3. All of that equals 0. Now solving this, I know e to the x is an exponential function. It can never equal 0, so I don't have to consider that. X squared minus 3 can equal 0, though. If I add 3 and square root both sides, I have plus or minus root 3 as my two critical values. So I'm going to put those on a number line, which I'm going to label as an f prime number line here. So we have negative radical 3, positive radical 3, and I'm going to do a little sign analysis to see where f prime is negative or positive. So plugging in a number less than negative root 3, that would be a number like negative root 4, which is also called negative 2. Plugging that in to my simplified f prime here, e to the x is positive no matter what, so I don't have to worry about that. X squared minus 3 could go either way. So if I plug negative 2 in, that's going to be 4 minus 3, which is a positive. A number between negative and positive root 3, how about 0? That would give us 0 minus 3, which is negative. And then if I plug in something bigger than root 3, like 2, that gives us 4 minus 3, which is again positive. Taking a look at this, f prime is clearly positive from negative infinity to negative root 3, and from root 3 to positive infinity. So I can write from this that f is increasing from negative infinity to negative root 3, union root 3 to infinity. Or you could say x less than negative root 3, or x greater than positive root 3. For this last problem part, they want the intervals on which the graph of f is concave down with analysis. So for this, I need to know where f double prime is negative, but I need to find f double prime first. So here is f single prime from part B. This was the simplified version of it, which I'm really glad now that I simplified it at some point. So for this, I'm going to need the box and ribbon, a product rule to take the derivative of this. So we've got e to the x and x squared minus 3. Derivatives are e to the x and 2x. Multiplying that out with the ribbon, I have e to the x squared minus 3, and I'll just leave that in a parentheses for now. And then we also have e to the x times 2x. Now I can factor an e to the x out of this, just like I did in part B. So that leaves me, and I'm setting this equal to 0 to find critical values. So that leaves me, if I factor out that e to the x, with an x squared, a positive 2x, and this minus 3. I'm just writing it in order right away so I can factor it. So let's see, two things that multiply to negative 3 and add up to 2. Well, first off, this e to the x we know can't be 0. But now factoring this is going to break up into, let's see, x minus 1 and x plus 3. So that means that our critical values are positive 1 and negative 3. Well, time to put those on a number line and do some sign analysis. I labeled this f double prime, and we've got negative 3, positive 1. Let me test something less than negative 3, like negative 4. And I'm just going to plug it into this factored version here. E to the x we know is always going to be positive because it's an exponential function. So just plugging negative 4 into these parentheses, we've got a negative times a negative, so positive for that first interval. Between negative 3 and 1, I can test 0. That's a negative times a positive, so negative. And bigger than 1, how about 2? Positive, positive gives us a positive. Since I've shown that f double prime is negative on the interval from negative 3 to 1, I've shown that f is concave down from negative 3 to 1.